I'm very glad Sander accepted our invitation to this new installment of the lunch seminar series at of the Logic Group at the Department of Philosophy in Milan. So I very glad Sander is here. Sander is currently a postdoctoral Humboldt Fellow in Munich at the Center for Mathematical Philosophy. Is already a very extensive academic life. He comes from Leuven, where he got a PhD in the topic of which is also on the topic of which is also talking about today, namely actual causation. After that, he was at Cornell, working with Joe Halpern, then Leipzig, and then Utrecht, where he also worked on a project in moral responsibility and issues in AI. So I came to know personally Sander last year when we were co-participant in this research group at NIAS in the Netherlands, and we're going to co-organize a workshop at the Lawrence Center next month on explainable medical AI. But today we'll talk about a recent, I think this is material from forthcoming papers or paper of him in the Journal of Philosophical Logic by the same name, the same title. So Causal Sufficiency and Octal Causation. So thanks, Sander, for coming, and the floor is yours.
Thank you, Giuseppe. Thanks a lot for inviting me. And I'm hoping now that everything goes smoothly. It's very weird for me because all I see is my own screen. I don't see any participants. So if at any point my connection goes off or something, I won't notice and I might just keep talking without anyone listening. But I'm assuming that that won't be the case. And as Giuseppe pointed out, indeed, this is a paper which has recently been accepted. So hopefully there's not too much criticism, because that would be too bad, because I'm not going to change it anymore. And I'll get going as quickly as possible, because there's a lot of material to cover. So first, I'll give you a sense of what the problem is, the background that's required to understand what's going on. And I'll have to then introduce the formalism that I'm using, which is the causal models, in particular structural equations modeling, which I use to define all the notions that I'm working with, in particular the notion of causal sufficiency, which is obviously distinct from logical sufficiency, and which is a necessary prerequisite, I believe, and many people believe, for offering a proper account of actual causation. So once I've established the definition of causal sufficiency, or to be more precise, established several definitions, I'll show how those can be used to define actual causation. And in fact, we'll get from that 12 distinct definitions of actual causation. And I'm going to argue that one of those is better than all the others. And that's the fifth section, the results. So how do we filter out now, out of this entire spectrum of definitions, the one which is most suitable, most appropriate? And so I'll be presenting in form of certain forms of information that allow me to argue that the definition I've chosen is superior in the form of, and that information takes the form of theorems, but also certain examples. And in particular, of course, I'll be comparing my definition to existing definitions. So I won't be reinventing the wheel. My starting point will be a very familiar one for anyone who's worked on actual causation. And that'll become more clear as I delve into the introduction. So I'll go there right now. Actual causation, for those not familiar with the terminology, simply put, it refers to the causal relation that holds between particular events. So causation occurs in natural laws. There's many laws which somehow connect causes to their effects, but those laws speak of general connections. So for example, smoking causes cancer. It doesn't mean that every person who smokes gets cancer, nor that every person who smokes and has cancer got cancer because of the smoking. To find out whether a particular person who smokes and has cancer got cancer through the smoking, that question, did this particular person smoking cause this particular person's cancer? That is a question of actual causation. So it's a causal relation that holds between token events. And it's a notion which we use in everyday life quite often. So Giuseppe asking me to give a talk to you is a cause of us meeting online right now. And therefore, it's a very widespread underpinning of much of our knowledge, both in common sense reasoning, but also in science. And for a long time, philosophers have talked about this, but couldn't make a lot of progress. And in part, that was due to the lack of a language for spelling out causal relations properly. And I'm assuming, as most of you know, this has changed due to the work of Halpern Pearl, who in 2000 wrote his book Causality, in which he introduced causal models that allow us to very precisely speak about interventions and counterfactuals using causal Bayesian networks, but also using structural equations, which I'll introduce later, and therefore set off an entire field, subfield of artificial intelligence, which is by now, well, spanning all elements of science and of computer science. So in particular, the counterfactuals there are what matters for actual causation, because there's a close connection between the two. So take back the example of Giuseppe inviting me. If Giuseppe had not invited me, counterfactual, then we would not be meeting here online for this talk. Therefore, a very natural test for causation is the notion of counterfactual dependence. If the candidate cause had not occurred, would the effect have occurred? Now, in the book, in the 2000 book, and 2009, he wrote a second edition, Pearl also introduces a definition of actual causation using causal models. And he argues for this definition along, you could say, two different strategies. The first is a more conceptual foundational strategy, which says that, which builds on insights by Richard Wright, but also others like Mackey, who have had very similar insights, namely that in order for something to be a cause, what this means is that it's a necessary element of a sufficient set, the Ness intuition. And he makes some remarks about this, but then when he actually proceeds and gives his definition of actual causation, he kind of strays away from the Ness intuition and doesn't really come back to it anymore. In fact, many of the notions he introduces have very complicated names, let alone complicated definitions, like causal beams and sustenance, and very little theoretical justification is given as to why these notions capture some intuitive concept. In fact, in order to motivate his definition, what he uses mostly is a second strategy, which is giving examples, toy examples, and then alluding to our intuitions, saying, oh, my definition for this particular example gives the right answer. Therefore, it's a good definition. Now, his work has had a huge impact on researchers, both in philosophy and artificial intelligence, working on actual causation, and most of them have abandoned the first strategy and resort solely to the second strategy of giving it examples. Now, the problem is that, well, first of all, we can keep constructing examples forever. And second of all, many people have very different intuitions about these examples. And often the explanations for why a particular definition doesn't meet with someone's intuition is very ad hoc. So it's perhaps an endless debate that could continue forever unless we have some more principled way of looking at this. So concretely, what happened is Halpern joined up with Pearl, and they produced several definitions, which are variants of the original definition from the 2000 book, which have become very influential. In fact, many people, both in philosophy and AI, have proposed definitions which are somehow modifications of those Halpern and Pearl definitions. And so it's quite fair to say that that is a standard to which one should compare one's definition of actual causation in order to make an argument that it's a good definition.
So is it okay to ask Just a clarification question, yeah. On the example, I'm really not familiar with the whole idea, so maybe it's a completely stupid question. So you gave the example of Giuseppe inviting you to this thing and this being a sufficient, sorry, you said a necessary condition for you actually being there. So it just caused your talk in this sense. But as you were speaking, I was thinking, well, it's sufficient that Giuseppe invited you, but it's not necessary. Paolo could have invited you. And that invitation would still be sufficient for you delivering this talk. So I'm not exactly sure in that example, why do you say that Giuseppe inviting you is a necessary condition for the sufficient conditions for this? I don't know if I asked clearly my question.
Well, in this part, so there's 2 points. There's a general point, namely that this relation of counterfactual dependence in general is only a sufficient condition for causation, certainly not necessary, because that's in fact the realization of David Lewis, on which Pearl builds, that counterfactual dependence is far too strong. So the tricky part in defining actual causation came up once people realized that there's cases of preemption in which there is causation intuitively, but there's no counterfactual dependence. Now, as to this particular example, given everything we know about the world, we simply know it is the case that none of the other people invited me. So if we're looking at the counterfactual, which only makes the smallest possible change to the world, then that would be simply be the world in which everything else is as it is, but Giuseppe would not have invited me. And in that case, indeed, we wouldn't have this talk. So this is an important elucidation as well, namely that actual causation, questions of actual causation in this context are posed relative to a causal model. Well, I'll get to that in a second, but we're assuming already that we have a lot of information about the world and about counterfactuals, so that it's not a matter of uncertainty regarding what would have happened. Therefore, it's a conceptual question rather than an empirical question. Now, let me get back to what I would say is wrong with the current literature. I've already said certain things, namely that the NES strategy has hasn't received enough attention. In particular, although Pearl starts out with saying, yes, this NES intuition is very important and we should make it precise, he doesn't offer a definition of causal sufficiency. He also doesn't explicitly define necessity. So what I'm going to do is just go back to the beginning, propose 6 definitions of causal sufficiency, 2 definitions of necessity, and together those give 12 definitions of actual causation, and I'll argue that one of them is better than all the others. That's the setup of the paper. So to do that, I'll first have to say something about causal models, in particular structural equation modeling. I'm going to use the notation that's used by Halpern. It's a little bit different from Pearl's, but it's just the one I've gotten used to. And I'm also going to give this a rough sketch. I know you're logicians, so I'm going to be very careful, and I might not make everything as precise as I should. I'm also not going to use as many formulas, perhaps, as you would like in my talk. Because for most audiences, that's a bonus, but perhaps not here. So a causal model, M, that's a tuple, consisting of 4 elements. There's a set U, which is a set of exogenous variables. And those are the variables which tell you all the background information. We don't know what causes the exogenous variables, because those are not part of the model. We're just assuming that somehow the world is such that these exogenous variables get a certain value. That's our starting point. The set V represents the endogenous variables, and those are the variables regarding which we want to argue, we want to reason about the causes and the causal relations. So the exogenous variables get everything going, and then the endogenous variables are the consequences of that ultimately. R is simply a function that determines the possible values. So it represents the range of all the variables, which values they can take on. And then the last element is the most important, that is F, the set of structural equations. So each endogenous variable has one equation which tells you entirely how the value of that variable is determined by all the other variables. And in particular, this equation is asymmetric. So the right side determines the left side, right? So here's an example, X equals Y and Z. So this, assuming that we have Boolean variables, this simply states that y and z together are the parents of x, so that their values determine x, but not the other way around. And the fact that it's not the other way around, I'll make it precise in a second. But that's the causal part, that there's this asymmetry. Okay. Now, what are the kind of causal formulas?
Sander, just a logician question, trivially. Why do you use this double brackets notation? Is there a reason to have U, V, and R coupled as a tuple themselves?
Yes, that's because usually we introduce it in 2 steps so that U, V, R represents the signature of the model. Yeah, and I just took over that notation, but as such, in this context, it's not really important. Because what you can have is you can have 2 models which share the same signature, so they have the same U, V, and R, but have different equations. And to make that simple, we distinguish the signature from the equation. So the simplest formulas, atomic formulas, are simply a variable takes on a value. Then we consider propositional combinations of atomic formulas. And the causal part comes in by having syntax for interventions, which is the square brackets. And I use vector notation to indicate that there's multiple variables. So x with a vector is several variables. Likewise, small x with a vector means values for each of those variables. And the arrow there indicates that we're setting x to these values. And x, by the way, is a subset of the endogenous variables. So we perform interventions on endogenous variables. And so we can combine these propositional formulas with interventions. That's the last part here. And those are causal formulas that we're interested in. And they should be interpreted roughly as, after setting x to x, phi holds. Now, how do we make that precise? How do we interpret those formulas? Well, we do that, first of all, as I already mentioned, by having a particular valuation for all the exogenous variables. So that's what we call a context. So it's a particular assignment to all the exogenous variables. And also, I'm assuming we have recursive causal models for simplicity, meaning that once you fill in the exogenous variables into the equations, the values of all the other variables simply follow. There's a unique solution. And that's for simplicity. We could make it more open. We could have cyclic models, but for actual causation, usually people don't consider those. Now, if we have a context together with a causal model, that's what we call a causal setting. And this is, you could say, it has all the ingredients for one particular story, because it tells you what the background conditions were. It also tells you how then all the other variables are being determined. So that's the formal counterpart of a specific story regarding a person getting cancer and smoking, etc. Now, in a causal setting, a certain atomic formula is true, well, simply if that value is the value that comes out as in the unique solution to the equations. And obviously the same extends to propositional formulas in a standard way. The only novel element is the intervention. What does that do? So if a formula contains an intervention, this is interpreted as an operation on the causal model, an operation such that we're going to change the equations. In particular, if we have an intervention on the variables x, that means we get rid of the original equations for x. We don't care anymore what they were normally determined by, and we're just going to replace their equations by simply stating x gets this value, like a magical intervention, right? Like a small miracle where we just say, regardless of the normal causes of x, we're just stipulating from now onwards that x has these values. And therefore, this doesn't backtrack, and it's this, right? So there's an example next to make this clear. A very simple example, a causal model with 3 equations and 2 exogenous variables. And if I don't mention this, then it should be obvious from the context that the variables are binary. That's just for simplicity. Now, if this is our model, and we're looking at a context in which ux and uy both get value 1, then it's clear that this causal setting satisfies x, y, and z being 1. If we now intervene and set x to 0, what happens is the top equation goes away, and we just state x equals 0, and we then forward track all the consequences of that, one being that z equals 0. Now, this isn't a good example to illustrate what I was just about to, what I was saying, namely that we don't backtrack. What I can tell you now, let's say we intervene on z. Let's say I consider intervention z becomes 0. Now, normally, if these were regular equations, the only way z could be 0 is either x or y being 0. But in this case, we don't do that. We just replace the equation for z, just stipulate that it's 0, and it doesn't have any effect on x and y. That's the causal part of it, which makes it special. Okay, now that's hopefully enough background. The general form of the definition of actual causation takes this is the following, and this is what Halpern and Pearl use, and I think is a sensible general form, namely that to state that something is an actual cause, first of all, the cause here consists of a vector, but the effects, I'm only considering atomic effects. I give reasons in the paper why that's the case. I'm not going to go into those. Halpern and Pearl also consider more complicated effects. Now, there's 3 conditions which are necessary and sufficient for something being actual cause. The first is a trivial requirement, namely that the events that we're talking about actually happened. So in the causal setting we're considering, it is indeed the case that the cause was there and the effect was there. The second condition is what all the trouble or the interesting stuff happens. So I'm going to talk about that later. The last condition is a minimality condition. Simply put, we don't want to add redundant elements to X which don't have any role to play. So we're going to look at a minimal set only to satisfy the definition. So AC2, the second condition, that's where all the trouble lies. I'm not going to spell out the HB definitions. I'll just give you the simplest way of characterizing them. So the original one came from a paper in 2001, which was already a modification of the definition that Pearl gave by himself in his 2000 book. And it has 2 subconditions for AC2, A and B. And A can be interpreted as a necessity condition. B is just a very complicated condition. Let's keep it at that. In 2005, they realized that there were counterexamples, so they gave a modified version of the definition. It kept the same necessity condition, but it made the complicated condition strictly more complicated. Then recently, well, not so recently anymore, in 2015, Halpern by himself suggested another modification because, again, there have been many counterexamples to the previous version. And this new version only has one condition, and it's quite a simple condition. Yet, nowhere in their work do they justify that the complicated condition is somehow a sufficiency condition. In fact, I would state that it's very harsh to characterize it as a sufficiency condition. And I go into that into the paper. Now, like I said, I'm going to start afresh and say, we want to fill in these conditions by being explicit about the fact that we're using the Ness intuition. So you should have a sufficiency condition and necessity condition. Just some notation which I used for to make it shorter. If values are superscripted by a star, it means I'm referring to values that are actually occurring in the setting, the actual setting. If I'm using superscript prime, it means that those are all values which are counterfactual. So they did not occur in the actual setting. And this is useful for spelling out the formulas because we want to be talking about actual values and counterfactual values. So the first element here is that we want to express sufficiency. So being a necessary element of a sufficient set means that there is a set W so that the actual values of W together with the values of X are causally sufficient for the outcome. Then necessity, I'm not spelling it out anymore, I'm simply saying that somehow X is necessary for the sufficiency of the set we were talking about. And therefore the trouble comes, or the challenge lies in how do we define sufficiency? Now the starting point is that in a causal setting, if we want to say that some setting is causally sufficient for another setting, this should be interpreted as if we were to set X to the values X, which happens through an intervention, then it is the case that y takes on the value y. That's the minimal requirement. But there's still lots of things we haven't made precise here. We haven't said anything about all the other variables. So there's several options you could have. And in the paper, I give 6 options, but you could even come up with more. And I suggest certain further possibilities because there's a general recipe that goes into defining sufficiency in this manner. I'll just here mention the 2, you could say, most obvious choices. Namely, one is, now I'm getting into trouble because I can't see the entire slide, but I'll remember it. So the strongest possible option is that in all contexts, so that means for all background variables or background settings, sorry, so all settings U, if we set x to the value x, then y takes on the value y independent of the values of all other variables. And so the part independent of the values of all other variables, that means even if we play around with the other values through interventions, it still doesn't matter. We're still going to get y equals y. So that's a very strong form of making sure that y happens. The weakest form would simply be, rather than requiring this to hold in all contexts, it holds in some contexts. And rather than being able to manipulate all the other variables, we're simply saying, don't touch the other variables. Just let them be. I'll just give you now, I spell out in more detail 2 notions of sufficiency which are important for my purposes. So the first is the one I already mentioned, the strongest form, and I call it direct sufficiency. And the reason for that is that it only applies, well, if you add to this a necessity condition, then you'll find that it always applies to parents and children, so variables which are directly related to each other. And this definition here is merely spelling out what I've just said, so that C represents all the other endogenous variables. We can intervene on them in whatever way we like. It's still going to be the case that y takes on the values y. Now, the problem with this is that it's too strong in the sense that intuitively, there's examples where we want to say something is causally sufficient, and yet this definition is not going to capture it. Take a very trivial causal model where z equals y and y equals x. And remember that these equations are supposed to be read from right to left. Now, I would say if anything is going to count as causal sufficiency, I would want to say that x taking on value 1 is causally sufficient for z taking on value 1. Yet, applying this definition, that doesn't hold, because y, the intermediate variable, if we intervene on that, then the influence from x to z is broken off. Therefore, x1, e being 1, is not directly sufficient for z being 1. Now, if you want to be more tolerant with your notion of causal sufficiency, this is not going to do. And what is an obvious suggestion? Take a transitive closure, because that's what I've used informally as well for my reasoning. X determines y, y determines z, therefore x determines z. And that notion of sufficiency is what I call strong sufficiency. And I'm not going to read it. Essentially, it does what I just said. It takes a transitive closure of direct sufficiency. So that if we look at the same example, we do get that x equals 1 is strongly sufficient for z equals 1. Now, an important clarification is that this sufficiency occurs along a network. So the network consists of all the intermediate steps that you're taking to get from x to z. And so in this case, the network would consist of y and z, because you went from, those are the variables that you came across. And taking into account the network, I think is an important element of saying what form of sufficiency or what exactly the relation is between the cause and the effect. It's not just that it's strongly sufficient, it's that it's strongly sufficient along a particular network. Good. Now we've got sufficiency, and like we've already seen, that was essentially what we needed to define actual causation, so we can just plug it in. So remember, this is the first part of the general definition of actual causation, and what was required was to fill in AC2. So that's what we are going to do right now. And there's 2 conditions, as I pointed out, the sufficiency and necessity condition. I'm going to start with one interpretation of necessity, which is contrastive in nature. Or you could also say it's counterfactual in nature, because it explicitly refers to counterfactual values of the candidate cause. So it refers to values x prime. Now I'll start with the second condition, B, because that's easier. It just says that plug in your notion of sufficiency, and then it just states there is a set of actual values such that together with x, they are sufficient for y along a network. The necessity condition then states that there are counterfactual values so that this is no longer the case. But to state that it's no longer the case should be made more specific. In particular, it is not the case that these counterfactual values of x, together with our values w, are sufficient for y along the network, but it's also not the case that they are sufficient for y along a subnetwork, so along a subset of the variables of n. The reason why I'm adding that latter clarification is that I wouldn't want to consider the values x, the actual values necessary for the sufficiency, if there's counterfactual values which can accomplish the same end with less means. So if it can accomplish the same with a smaller network, then I don't want to call x sufficient for y along that network, because all it's doing is making sure the network becomes larger. Okay.
Sander,
yes?
Can I ask something?
Sure.
You might have said it and I might have missed it, but this means that you're assuming that you have complete list of possible causes such that you can identify all the counterfactuals for which you can say using this cause is not sufficient for my effect. Is that right? So there's some sort of completeness assumption here on the possible causes.
Well, that's what yes, that's an important point that goes into the causal model. So that's why I said earlier that we're already going to assume that our causal model is an accurate representation of the world. So if your causal model doesn't take into account a whole bunch of variables which are actually quite relevant, then yes, this definition is not going to give the right answer. But there the flaw would lie with the causal model. And of course, there's always certain element of subjectivity, you might say, as to, oh, should we include these variables? And there's in fact a lot of discussion also on that, because you don't want to make it your definition too dependent on a particular causal model. So that's certainly a discussion to be had. But for the sake of this paper and defining actual causation, I'm assuming that the causal model that we have is already an accurate representation of the world. And so therefore we only need to look at all the variables and their values in that model. Okay, so this is the definition. Namely, well, this is the general definition, and then we can fill in sufficiency according to any of the 6 options that I've defined. And that gives you 6 definitions of actual causation. Now, I've indicated here that I'm using contrastive necessity. An alternative would be to use minimal necessity, as I call it. And that could also be applied to each of the 6 notions of sufficiency, therefore giving 12 definitions in total. Now, what is the difference? For the contrastive notion, we required there to be counterfactual values x. The minimal notion is much simpler. It just says if you get rid of x, the remaining variables w are no longer sufficient. And they're both, you could say, sensible interpretations of necessity, and I leave it up to the results to determine which one is the most useful or the most sensible one. So all in all, if we combine these 6 notions of sufficiency and 2 notions of necessity, we get 12 definitions. I will simply tell you which is the one that stands out, namely the second one. It has a contrastive interpretation of necessity, so it's counterfactual. It focuses on the actual context, so it only focuses on the context that we're looking at right now, rather than requiring something to hold over all possible contexts. And it uses a strong notion of sufficiency, meaning it uses the notion I spelled out, which requires a network. And if you were to write it out, it looks like this, which I agree looks horrendous, but hopefully by giving you the elements out of which it's constructed, at least you can make intuitive sense of why it's a sensible definition. And also there's some further results which allow you in many cases to use a simpler definition as a stand-in, because there's cases in which this definition reduces to a much simpler one, which I offer in the paper.
Maar ik ben nu een praatje aan het luisteren.
Oh, sorry? Oh. Or that was, I'm assuming that wasn't referred to me. All right, results. So first, note that we have, for the moment, 15 candidate definitions of actual causation, namely the 12 that I've just defined and the 3 HP definitions. So that's 15 in total. What I'm going to do is get the counter from 15 to 1. So by selection, I'm going to dismiss definitions because they have certain bad properties. Definition 7, that's easy. It is impossible to satisfy. So I'm going to get rid of that. And the first theorem tells you that a bunch of these definitions are actually equivalent to each other. Right? So this notation is simply short for if something is a cause according to the one definition, it's also a cause according to the other definition, and vice versa. That's what these equivalences are stating. And note that the first part here, modified HP, so the most recent definition of causation from Halpern, is actually equivalent to one of the definitions that I've defined. So you could say that at least, although Halpern isn't explicit about this, he has implicitly used or formalized the Ness intuition, because it fits the description of necessary and sufficient conditions. Okay, the other takeaway message from this theorem is that there's 6 definitions that we can get rid of because they're just equivalent to the other ones. So we only have 8 left at this point. An important element which comes up with Halpern's definition is that he also looks at parts of causes. So if a cause consists of a vector of variables, then a part of a cause is any conjunct that occurs in the conjunction. So any particular variable that occurs in that entire vector is a part of a cause. And essentially, Halpern says that we should treat part of cause and cause synonymous. I'm pointing that out because some of the results that I formulate make use of the notion of part of a cause. And I spell out in the second theorem all the relations that hold between the remaining definitions, and the only one, and these are the only relations that hold. Now, the first 2 statements are already well-known results from Halpern and Pearl. It's only the latter 4 which I've proved in the paper. And those are interesting when you're applying definitions, when you're trying to compare strengths, that's a useful result. But as such, it doesn't allow us to dismiss any definitions yet. To get our counter lower, I'm going to invoke a principle. And this is a principle which captures the intuition that I started out with, namely that counterfactual dependence is sufficient for causation. And that intuition goes back to David Lewis. Well, sorry, it goes back to Hume. David Lewis is the first to try to make it formal. I'm only going to focus here on causes that are atomic, so just one variable x. And the principle simply states that if it's the case that changing x changes y, then x causes y. Now, if we accept that principle, which certainly Halpern and Pearl do, but also most other authors, then there's already 2 more definitions that we can get rid of because they do not satisfy it. So we have 6 definitions left. The next part is to look at the work of Halpern and Pearl themselves. And as I said, there's so many intuitions out there that it's hard to have any objective standards. So what I try to do is look at the reasoning and the intuitions of Halpern and Pearl themselves. And on their own account, does my definition do better or worse? So looking at their papers, first of all, they themselves dismissed the original one. That's why they came up with updated HP. But also there's very good reasons to look at, there's very convincing examples in their papers to show that definition 4 and 8 are very bad. Then afterwards, Halpern defined modified HP, and on the grounds of that dismissed updated HP. So that leaves us with only 2 definitions, namely modified HP and definition 2, which according to all of the examples discussed by Halpern and Pearl do equally well, or at least equally well. I make a subtle point in the paper that even on some of the examples discussed by Halpern himself, my definition does better, but that's a minor point. A more important point is that there's examples in which Halpern's definition doesn't do very well. I'm only going to give you, I'd say, one of the most intuitive, which is one that was brought out by a review of Halpern's book by Glimmer and Rosenberg. And it goes as follows. The equations are, again, very simple. So we have that y equals x or d, all the variables are binary, and x equals d. And we're looking at a context in which d equals 1. So in other words, all the variables get value 1. And just looking at the equation for y, this seems to be a standard case of overdetermination. There are two events which occur. Each of them by themselves are sufficient for the effect to occur. And they are each equally powerful, you could say. And indeed, if you look at all the definitions that I've considered, and all the definitions, well, I haven't looked at all of them in the literature, but let's say all the most well-known definitions in the literature, they all agree that both x being 1 and d being 1 are causes of y being 1. So they both overdetermine y. The only exception is Halpern's definition. It says that x being 1 is not a cause of y being 1. Now, Glimmer and Rosenberg give the following example as a story that could go along with these equations to convince you that this is very counterintuitive. Imagine that D represents a gang leader who orders every member of his gang to join him in shooting a victim. And so rather than now having just one X, imagine that there's 10 X's, X1 to X10, and they all together shoot victim. And one bullet would have been sufficient to kill the victim. Now, according to Halpern's definition, only the gang leader and his order is a cause of the victim dying. And a fortiori, he's the only one who's responsible under the assumption that responsibility requires causation. And I quote from Glimmer and Rosenberg, "This is a morally intolerable result. Absent a plausible general principle severing responsibility from causation, any theory that yields such results should be rejected." Now, I agree with their assessment, but as I said in the paper, I also consider other examples, and in particular, I consider examples which are only very small. I consider 6 examples which are extremely similar to each other and argue that the modified definition doesn't have a very consistent way of handling them. Regardless of whether the answer for one particular example is intuitive, the fact that changing the example in a very trivial way changes the definition's judgment, I use that to argue that it's not a plausible definition. And therefore, since those were the only 2 remaining ones, if we dismiss modified HB, only my definition 2 is remains. Of course, I cannot exclude the fact, and that other examples come up or other principles which might rebut that definition, but for the moment, at least, I would argue that it stands as an improvement. So let me summarize what I've been trying to convince you of, namely that the Ness intuition, which actually has a long tradition in history, in philosophy, in particular in legal philosophy, is important, and it was on the right track, and Pearl was very correct to start out with it. But we should reestablish its importance also when we come down to the formal details, rather than merely a source of inspiration. I've made this concrete by offering several definitions of causal sufficiency, and those definitions then give you a recipe for defining actual causation. So the definitions of sufficiency that I've given only amount to a limited number of possibilities. There's even more possibilities that you could construct with the same recipe, and therefore there's an entire spectrum of definitions of actual causation that you could come up with. And I've argued that one definition that we can construct using this recipe is superior to the existing definitions, and therefore forms an improvement over the existing definitions as well. And that sums it up. I am now open for questions.